The next chapter is on waves. We will start with chapter 5.1 basic waves, and in this you will learn the very first basics of waves. This is the very first lesson in the IAS Physics course on waves. And by the way, in almost every chapter you have the definitions at the end of the chapter, so these definitions are very important. See, wave, displacement, amplitude, frequency, wavelength, period, phase, wave speed, wave equation, and you should know these definitions. What is a wave? A wave is a means of transferring energy via oscillations. A wave is a means of transferring energy via oscillation. So the energy is transferred from one place to another place via oscillations in a wave. Then this is the displacement of a wave when it comes to a wave. Then we have amplitude, frequency. You would have seen this equation in the O-level class also. Frequency equals 1 over the period. F equals 1 over t. And in this case we can say frequency is the number of complete wave cycles per second. Number of wave cycles per second is the frequency. Then displacement is the position of a particular point on a wave at a particular instant in time measured from the mean equilibrium position. So I think there was a diagram also here. So this is very important. In the O-level class also you would have seen this. So this is the equilibrium position. You see the x-axis here. That position is the equilibrium position or rest position of the wave. That means when the wave eventually dies, that means when the energy of the wave decreases, this amplitude can decrease. Amplitude is the maximum height of the crest. So from here to here is the amplitude. That is the maximum displacement. Now this axis is displacement, this axis is time. So if it's a displacement versus time graph, the height of this crest, these are called crests. You can see it's labeled here. The bottom parts are called troughs. T-R-O-U-G-H, trough. The height of the crest is the displacement. Is the amplitude. The maximum height of the crest is the amplitude, or we can say the maximum displacement is the amplitude. So that's the definition of amplitude. Amplitude is the maximum displacement. Let's go back to the definitions here. Displacement is the position of a particular point on a wave at a particular instant in time measured from the mean or equilibrium position. So what happens is, with time the energy of the wave can decrease, and as a result the displacement or the amplitude becomes lesser and lesser. The amplitude, the height of the crest and the depth of the troughs become lesser and lesser, and eventually it becomes zero. The displacement or amplitude both become zero. Now the displacement is from the equilibrium position to here to here. So you can see the displacement here is zero, and over here the displacement is maximum and it is equal to the amplitude. Amplitude is the maximum displacement. So you can see from here to here, when we go along this crest, the displacement increases and it is maximum here. It is zero here. Then when we go from here all the way this way, the displacement, measured vertically like that, the displacement, the vertical height, decreases and then it becomes zero. So remember, the displacement is from the x-axis vertically to the red curve. Okay, so this is the red curve or the wave. So from here to here, that is displacement, the vertical height. Okay, so if it's here, then from here to here, that is the displacement. Then from here to here, that is also displacement, but the displacement here is negative. You can see the y-axis is the displacement, here the y-axis is negative. Then here we have maximum negative displacement, and period is the time for one complete wave cycle. So if we start here, then we complete one wave cycle, that is the period. Period is the time for one complete wave cycle. Then let's see the next one. So now you know what is displacement, you know what is amplitude, you know what is a wave. Amplitude is the magnitude of the maximum displacement reached by an oscillation in the wave. Frequency is the number of complete wave cycles per second. Frequency equals 1 over the period. Then wavelength is the distance between a point on a wave and the same point on the next cycle of the wave. Now, a common mistake that students make is they sometimes label from here to here as the wavelength, but that will be the wavelength if this is the distance axis. So here, from here to here, yes, that is the wavelength. See, it's labeled here. So you have to look at what the axes are. I have mentioned this previously also. Whenever you get a graph, first thing you have to do is look at what the axes are. In this case, it's a displacement versus distance graph. So from here to here, that will be the wavelength. But here, it is a displacement versus time graph. So then this will be the period. So remember, if it's a displacement versus distance graph, from one point on the wave to the next point on the next cycle, we can phrase it the way that it is mentioned here. Wavelength is the distance between a point on a wave and the same point on the next cycle of the wave. The same point on the next cycle of the wave. So if we start here, then the next one is here. Okay, so this is the time axis, then therefore this will be the period. If this was the distance axis, then from there to there it will be the wavelength. Now we can also start here. If we start here, then from here all the way to here, from here all the way to here, that will be the wavelength. We can even start here. So we start here, we go all the way to the next point there. Okay, so you see the wave cycle completes one whole cycle from here to here. So horizontally that distance is the wavelength. So you have to know this. Then we have period. Also the time period is the time taken for one complete oscillation at one point on the wave. Period equals 1 over frequency. Then we have phase is the stage a given point on a wave is through a complete cycle measured in angle units. Angle units radian in this case. Okay, so we have one whole cycle that is 360 degrees, and if you convert it to radians, which is another unit of angle, then it will be 2 pi radians. Okay, so 2 pi radians. Now if it is half the way, then it will be pi radians or 180 degrees. So phase is the stage a given point on a wave is through a complete cycle measured in angle units. Okay, again phase is the stage a given point on a wave is through a complete cycle measured in angle units radians. By the way, these definitions are in more detail over here. You can see phase, the stage a given point on a wave is through a complete cycle. Phase is measured in angle units as a complete wave cycle is considered to be the same as traveling around a complete circle, that is 360 degrees or 2 pi radians. Okay, so one whole wave cycle is 360 degrees or 2 pi radians. So the stage a given point on a wave is through a complete cycle, that is phase. Phase is measured in angle units. As a complete wave cycle is considered to be the same as traveling around a complete circle, that is 360 degrees or 2 pi radians. No standard SI, no standard symbol. SI unit is the radian. Again, if we look at this, for example, now let's say from here all the way to here, you can understand that is one complete wave cycle. So if something is, let's say here, then the phase is pi radians, because pi is 180 degrees. Now you can see from here all the way to here, that is 360 degrees. Now you can also think, if you turn your head all the way round, okay, so that you're facing forwards, then you turn your head, or you turn your whole body with your head all the way back. So you see back, that is 180 degree turn of your head. So you continue turning and then you come to the same position. You complete one entire rotation or rotation, and then you are facing the same direction. So that's a 360 degree turn. So something like that. Here all the way to here, you can see you came back to the same position on the wave. So that is 360 degrees. Now half the way is 180 degrees. Okay, so if something is over here, then its phase compared to the whole thing is 180 degrees. But what about here? When it is here, the angle is 90 degrees, right? See, it's half of 180. It's quarter from here to here. This is a quarter of 360 degrees, which is 90 degrees. So from here to here, that's 90 degrees. Then 180, 270, 360. So if something is here, its phase is 90 degrees. We can see more details, but now I think you understand phase. You would not have seen that in the O-level class. Again, let's quickly read this. The stage a given point on a wave is through a complete cycle. Phase is measured in angle units. As a complete wave cycle is considered to be the same as traveling around a complete circle, that is 360 degrees or 2 pi radians. So we can say 90 degrees is pi over 2 radians. 180 degrees is pi radians. You can remember the conversion factor. 180 degrees equals pi radians. So with that you can see what the other angles are in radians if they are given in degrees. So remember the conversion factor. 180 degrees equals pi radians. Okay, let's see this. Wave speed is the rate of movement of the wave, not the rate of movement within oscillations. Okay, so we have the wave equation. You would have seen this in the O-level class also. Wave speed equals frequency times wavelength. V equals f lambda. V equals f lambda. F is the frequency, lambda is the wavelength. V is the wave speed. The unit is meters per second. Frequency has the SI unit hertz. Wavelength has the unit meters. Okay, so you should know all these equations. These are all in SI units. Time period equals 1 over frequency. Frequency equals 1 over period. And all these definitions are important. And here it's at the last part of the chapter. So now if we go up a little, you can see this a little more in detail. So let's go through this because this is very important. There are a number of important properties of waves that scientists measure for various purposes. In most cases, you can determine these from the graphs shown in figure A and figure B. So here is one graph, figure A. We have actually two there. And you can also see the labels here. Here we have the horizontal label, which is the wavelength. Here we have the vertical amplitude. So this is a displacement versus distance graph. That's why this is wavelength. And I told you, if it's a displacement versus time graph, then for one whole cycle, that will be the period. Here it's the wavelength. Okay, so displacement is the position of a particular point on a wave at a particular instant in time measured from the mean or equilibrium position. We also call it the rest position. Symbol varies often x varies. Okay, so I mean we use x, we use s. You know, in the case of motion, you would have seen the SUVAT equations, SUVAT equations, the equations of motion for uniform acceleration. Remember, there we used simple s for displacement. We can also use x, the letter x, simple x for displacement. Okay, then amplitude, the magnitude of the maximum displacement reached by an oscillation in the wave. Symbol capital A. We use capital A for amplitude, and also it's a distance measurement. So the SI unit is the same as the SI unit for displacement, distance, which is meters. And if you look at this diagram, you can see from here to here, that will be the amplitude, which is the maximum displacement. Okay, so if you consider this point on the wave here, from here to here, that will be the displacement. From here to here, that will be the displacement. Here to here, that maximum displacement. Here the displacement is 0. Here the displacement is 0. So remember, it's always measured vertically upwards or downwards from the x-axis. Now even here it's displacement. Okay, so from here to here also it's displacement. But the only difference between these two graphs and this one I'm telling the same thing again and again because it's important, and a lot of students make the mistake of labeling this over here. Remember, if it's the x-axis, this will be the wavelength. If it's the if the x-axis is distance, it will be wavelength. If the x-axis is time, it will be period. Okay, the y-axis is the same in both cases, that is displacement. Okay, so the next one, amplitude, frequency. By the way, the magnitude of the maximum displacement reached by an oscillation in the wave, that is amplitude. The number of complete wave cycles per second. Now we are talking about waves, that's why we are saying wave cycle, but frequency can be applied to other things also. So frequency is the number of cycles per second, number of oscillations per second, number of revolutions per second, number of rotations per second. So it's something per second, some complete cycle per second, that is frequency. Now in the case of waves, we have wave cycle. So the frequency is the number of complete wave cycles per second. This may sometimes be measured as the number of complete waves passing a point per second. So we can say it that way also. So if you have a certain point here, now imagine even this, you can have the wave going to the left or to the right. So how many waves pass this point per second is the frequency. So number of wave cycles per second is the frequency. So it's number of wave cycles per second. So something per second. So per second we have the unit hertz, capital H, simple Z. The symbol is F for frequency, the unit is hertz, the symbol of the unit is this. Wavelength, the distance between a point on a wave and the same point on the next cycle of the wave. For example, the distance between adjacent wave peaks, symbol lambda, SI unit meters. Okay, so I already showed this to you over here, you can see. So we start on one point on the wave, we complete one whole cycle, then to the next point. That horizontal distance is the wavelength if the x-axis is distance. Okay, then okay, this wavelength, the distance between a point on a wave and the same point on the next cycle of the wave. See, same point on the next cycle of the wave. For example, the distance between adjacent wave peaks. This is one wave peak, or also called crest. Okay, peak, or some books call crest, some books call peak. So from the top of one peak or one crest to the top of the next or the adjacent crest or peak, that is the period if it's a time axis. But if it's a distance axis, from here to here, that will be the wavelength, because this is a distance axis. So wavelength. So you can see from one point on a wave to the same point on the next wave cycle. So that's why I said if we start here, then we have to go to there. So from here to here, that is the wavelength. For example, the distance between adjacent wave peaks, period, the time taken for one complete oscillation at one point on the wave. This will also be the time taken for the wave to travel one wavelength. So one wavelength to pass, or one wave cycle to pass, the time taken for that is the period. Okay, so I went through phase, then wave speed. You have learned this in the O-level class also. This is a very important equation. Wave speed is measured in meters per second, frequency is measured in hertz, wavelength in meters. The rate of movement of the wave, the same as speed in general, symbol V or C for speed of electromagnetic waves. Now we use the letter C for the speed of electromagnetic waves. Remember, the main equation was V equals F lambda. If it is electromagnetic waves, we use a C equals C instead of V. C equals F lambda. The rate of movement of the wave, the same as speed in general, symbol V or C for speed of electromagnetic waves. You can find the speed of a wave from distance divided by time, as with the speed of anything. However, as each wave has a certain wavelength and the frequency tells us how many of these wavelengths pass per second. See, how many of these wavelengths pass per second. So there has to be a time there. Just with the distance alone, you can't find the frequency. However, as each wave has a certain wavelength and the frequency tells us how many of these waves pass per second, you can also find the speed by multiplying frequency and wavelength together. So that is what is indicated in this equation. This is often referred to as the wave equation. This equation is very important. You have seen that in the IGCSE or O-level classes also, and we will be using this equation a lot even in the A-level or IAS IAL classes. Okay, let's go to the beginning. So what is a wave? I mentioned that earlier when we went through the definitions towards the end of this subchapter. So this is chapter 5.1.1 wave basics. By the end of this section you should be able to understand the terms amplitude, frequency, period and wavelength. Now you have learned that already. Define wave speed. Okay, so V equals F lambda equation was used. Measure the speed of sound in air and use the equation, wave equation, V equals F lambda. Speed of sound in air. I think in the O-level class, IGCSE classes also, you would have learned several methods to find the speed of sound in air. And use the wave equation V equals F lambda. Explain how pulse echo techniques allow the measurement of distances. Echo is the reflection of sound. So if you go to an empty hall, you make a sound, then afterwards you hear it again, right? That's the echo. The sound gets reflected from the hard surfaces and the reflected waves come back to your ear. So initially when you make a sound, you hear your own sound, the sound you make, because it's close to your ear, you hear it first. Then the echo is the reflected sound wave that gets reflected by the walls. If you are in an empty hall, roof or walls or even the floor, then it comes to your ear. So that is the second sound you hear, which is the echo. Echo is the reflected sound wave. Remember, echo is a reflected sound wave. Okay, so explain how pulse echo techniques allow the measurement of distances. We will see the details. So if we know the speed of sound in a certain material, then we can use that and the time it takes for the sound to go and come back, and then we can use the speed equals distance divided by time equation to find the time that it takes, to find the distance. Okay, so we know the time, we can measure the time for the sound to go and come back, and then we can, if we also know the speed of sound in that material, in the air or in that particular solid, then we can find the distance. Okay, so pulse echo techniques. Energy transfer. A wave is a means of transferring energy via oscillations. Okay, so this is what a wave is. Whilst energy moves from one place to another, the wave causes no net movement of any matter. Okay, now for example, if it's a water wave, so imagine in the sea. Okay, a mechanical wave is one in which there needs to be some sort of material medium, a substance that oscillates to allow the transfer of the energy. For example, a sound wave or a human voice transfers energy from one person's vocal cords to another eardrum by repeated vibrations of air molecules. Now sound is a mechanical wave because it needs a material medium, but if you look at electromagnetic waves like ultraviolet, infrared, those don't need a material medium. Okay, so any wave that needs a material medium, sound waves, is a mechanical wave. So mechanical, it needs a material medium. Electromagnetic waves can transfer energy through repeated oscillations of electric and magnetic fields. That's why we call them electromagnetic. Electric and magnetic fields are vibrating or oscillating. Electric and magnetic fields, but these fields do not need matter to support them. Indeed, the interaction between electromagnetic waves and matter generally slows their transfer of energy. For example, light travels more slowly in water than it does in a vacuum. So what happens is generally slows the transfer of energy. The electromagnetic wave, interaction between electromagnetic waves and matter generally slows their transfer of energy. For example, light travels more slowly in water than it does in a vacuum. Okay, then these graphs I already explained. the wave motion can be the vibration of a wave over a certain distance as if frozen at an instant in time. So you see the wave, imagine you take a photo, so that instant is this, frozen in time. Wave motions can be plotted on graphs. A plot of the displacement against distance traveled for a wave as in figure A. So distance, displacement versus distance graph shows the physical scale of the oscillations and the movement of the energy. Okay, so remember, greater the amplitude, greater the energy the wave carries. And if it's a sound wave, higher the amplitude, louder the sound. Number of waves per second is frequency. Greater the frequency in the case of a sound wave, greater the pitch. Alternatively, a plot of displacement versus time as in figure B shows how the vibrations occur over time. Okay, so you can see plot of displacement versus time. This is how the vibrations occur over time. So time axis, displacement versus time. Here it's displacement versus distance. The oscillations of a single particle or point in a wave plotted against time. And we went through this. There are a number of important properties of waves that scientists measure for various purposes. In most cases, you can determine this from graphs shown in figure A and B. And these are very important, these definitions. I went through them already. And investigating the speed of sound. So there are several ways you can find the speed of sound in air, for example. And in all these cases, we can use this equation. Speed equals distance over time. So we can have a known distance. Let's say you make a sound, we have a known distance, the sound goes, hits that particular surface and comes back as an echo. So that way we can see, we know the distance, then we can time how much time it takes. Or there are other techniques, other methods also that you can use, and then you can find the speed of sound. Because we know the distance, we can measure the time, and we can find the speed using the simple definition of wave speed, that is a distance traveled by time. We can use a twin beam oscilloscope. So this is another technique. You can use a twin beam oscilloscope to find the extra time a sound takes to travel a short extra distance. One beam trace shows a sound picked by a microphone held 50 centimeters from the loudspeaker. So you have the loudspeaker emitting the sound, then you have the microphone that is picking up the sound. Okay, so the detector is the microphone, and the transmitting happens from the loudspeaker. The sound is sent from the loudspeaker. So from this, the time it's sent from the loudspeaker to the time it is received by the microphone, we can know that time, and we can keep the loudspeaker and the microphone at a known distance like 50 centimeters. The other trace shows the same sound picked up by a second microphone, so you can have two microphones. Don't think there's a diagram, but I think in the IGCSE or O-level classes, okay, so here is the diagram. Okay, so one is emitting the sound, the other is detecting the sound. So as soon as the sound is emitted, this has a trace for that. Then when the sound is detected, there is another trace for that also. So you can see investigating speed of sound in air. This is another technique that you can use. Now in your exam paper, especially in unit 3, they can ask you about this, the practical part. So whatever in this book where you see it under investigation, that is where you have the questions, or it's related to unit 3, paper 3, the unit 3 paper. So that's why the unit 3 content is spread throughout the chapters like this under these topics, investigation or experiments. The difference in the positions of peaks of the two oscilloscope traces shows the time taken t for the sound to travel the extra distance d. If we measure this carefully, then the speed of sound is given by this. It can be difficult to make accurate measurements of the screen of an oscilloscope, so we need to synchronize the traces to minimize the effect of random error in taking such a measurement. Okay, so we have different types of error: random error, systematic error, zero error, parallax error. You have to know about these different types of errors also, and how you can minimize it. Now in the case of random error, there is a way we can draw a graph, we can take several measurements, then once we plot the graph, we can minimize or get rid of the random error. So that's another topic. Firstly, with both microphones at the same distance from the loudspeaker, the two traces appear in identical phases, positions, in phase. If we slide the second microphone slowly away from the loudspeaker, we will move the traces out of phase with each other until eventually they come back to exact synchronization. At this point, the distance between the two microphones is exactly one wavelength, lambda. We set the frequency of the signal generator, and so the wave equation can be used to find the wave speed. Okay, so for more details on this, you can go through my explanation again, maybe slow it down a little or watch that, then you would understand this. You can also read this part. Okay, then pulse echo technique, again it's about sending the sound and getting the reflected sound, which is the echo. So animals can use this to find the distance to a certain object, like bats. They use this technique, echolocation. Okay, pulse echo technique. The natural habitat for bats needed to be woodlands. So instead of seeing, they're able to find the distance from the sound that is reflected, the echoes. Okay, and they fly through the trees 10 to 15 kilometers per hour depending on species. For catching insects, the bats need to be able to sense their locations precisely. While their vision is better than the old simile, blind as a bat implies, their well-known echolocation system using very high frequency 50 to 100 kilohertz sound pulses gives a much more detailed perception of the world at distances of less than 5 meters. At greater distances, the echo is attenuated. So attenuated means the decrease in the signal with time or with distance. Okay, so attenuation. The echo is attenuated too much for the bat to use. But how does it work? The bat will make a chirp through its nose. This sound pulse will typically last 3 milliseconds. When the sound hits nearby objects, it will be reflected back to the bat's sensitive ears, and its brain can accurately measure the time between pulse emissions and echo reception. The bat's brain has also evolved to instinctively calculate the distance to the reflecting object using the equation distance equals speed times time. Experiments with dolphins have shown that they use a similar echolocation system, but for them it is so sophisticated that dolphins can build up a mental image of the shapes of nearby objects they can see with sound. So you see, seeing with sound, because they can build up a mental picture by the sounds and the reflected sound wave. So echolocation. This is probably also true for bats to ensure that they eat an insect and not an insect-sized leaf. But dolphins can respond to experimental inquiry in a more conclusive manner than bats. Dolphin echolocation is sophisticated enough to make out the shapes of objects in murky waters. We have developed similar pulse echo ranging and imaging systems in a wide range of and imaging systems in a wide range of technological applications, from sonar on ships and submarines to air traffic control radar, medical imaging, and the measurement of distance to asteroids and to the moon. This is particularly useful in situations where other methods might be difficult or hazardous. For example, Venus has a very hot, high pressure atmosphere with sulfuric acid clouds that block our view of the surface. Mapping the surface uses a remote radar technique has avoided the need to land on the planet. So mapping the surface using a remote radar technique has avoided the need to land on the planet. Now here is an example. An air traffic control system sends out a pulse of radio waves that are reflected by a jumbo jet. The reflection is picked up by the radio dish 0.007 seconds after the emission of the pulse. How far away is the plane? So very simple. We can use this equation. Then the distance is speed times time. Speed of light by light, because this is an electromagnetic wave. Radio wave is an electromagnetic wave. All electromagnetic waves travel at the speed of light, which is 3 into 10 to the power of 8 approximately in air and also in vacuum. How far away is the sphere? So we are using this. Then that speed is known and the reflection is picked up by the radio dish this much. So after the emission of the pulse, okay, so the pulse is sent, then the reflected sound wave is heard after this much time. Okay, so it goes and comes back. So it goes twice the distance. Okay, so this is the distance to the object and back to the from the emitter to the object and then back to the emitter, where the receiver and the emitter, we can say they are at the same place. So in that case 0.007 seconds the radio pulse has traveled to the plane and back again, so the actual distance to the plane is half that calculated. Okay, so that's the end of this. Make sure you answer these questions, and the answers are also there. Make sure you check the answers after you do all these questions, then you will have a good understanding. And like I said, these definitions are important because in the exam paper they can ask you to write them down, they can test you. So when it comes to a definition, make sure you have all the points. That's why it's better to memorize the definition with understanding, because sometimes if you try to write it in your own words, you might miss certain key points where the marks are awarded for those points. So you can have a complete definition. Now even over here you have more detailed definition, and these are very important to make you ensure that you have understood the content. In other words, for consolidation you can do these questions as well. Okay, the next one is 5.1.2 wave types. We will see that in the next video.